Okay, good morning. I'd like to thank the organizers for the opportunity to speak at this very interesting symposium. The subject of my talk is Curvatronics in bilayer graphene and its link within an effective four-dimensional space-time. This is the result of recent work done in collaboration with Andrea Perali from Camerino, who's here, and Roberto Giambò, who is also in Camerino. I'd like to begin by posing the following question. What happens if we take a sheet of bilayer graphene, which is stacked in the AB fashion, and we bend it? So the conventional answer is the following. When you bend bilayer graphene, you're putting strain on the hexagonal structure, and this strain is equivalent to an effective magnetic field. So what you're going to get is Landau levels. And these Landau levels, they will change the energy. However, in particular, there is always an n equals 0 level. So the system that you obtain is not gapped. Well, today I would like to present an alternative answer, a new one, where the electrons at the Dirac points feel the intrinsic curvature of the surface. And because of this effect, one is able to open and close a gap by tuning the curvature. So this is a key effect to have electronic applications, so we want to call this Curvatronics. Okay. So I'll begin with a very quick review of Dirac fermions in graphene. So this is a all-purpose slide, just showing the usual properties of carbon-based structures, where you can have very different dimensionalities. The interesting part for us here, this is the graphene plane with the two parameters that are important in the present talk: carbon-carbon distance of the order of 14 angstrom, and the nearest neighbor hopping energy of the order of 3 electron volts. Now, graphene in nature doesn't come exactly flat. There are natural ripples. The ripple scale tends to be larger than the lattice scale, kind of smooth on the level of the lattice. Here is the lightning review, very quick, of how one obtains the Dirac equation in monolayer graphene, because I will need this in order to generalize to bilayer graphene. So one employs a tight binding model. This is a subset of the hexagonal lattice, and you can see the two inequivalent A and B points. In the tight binding model, what one has is basically a set of equations to obtain the energy, and one links the wave function in size of type A to that of size of type B, and T here is the hopping energy. So in matrix form, the equation of the tight binding model can be written in this way. There is the energy on the diagonal, and off diagonal you have this form factor that depends on momentum, where you're summing over these deltas, which are the displacement vectors from one side to the inequivalent other sides. And this you get because of the block form of the wave function. So you can solve the equation and find the energy spectrum, and in particular you discover the Dirac points, and close to them the dispersion looks linear, and one can say that close to that point they live Dirac gauss particles, and they have relativistic symmetry. These are the two Dirac points written in units of A. A is the carbon-carbon distance. When one analyzes the physics close to the Dirac points, energy is low, so you go to a continuum limit. You can expand the full momentum Q close to the capital K, which is here one of the Dirac points, plus a small momentum, and this is the Hamiltonian, the effective Hamiltonian that you get. In particular, one gets equation of the kind Dirac equation in 2 dimensions. Here the sigmas are the Pauli matrices, and the Fermi velocity pops out with from the parameters of the model. So again, A is the carbon-carbon distance and T the hopping parameter. Now, for the situation in bilayer graphene, what one is going to get is not direct fermions, but so-called Lévy-Leblond fermions. So let me show you. This is AB stack bilayer graphene. So there are two layers, and on top of every A atom of the bottom layer, there is a B atom on the top layer. And there is a hopping between the two layers. The parameter we call gamma is of the order of 0.4 electron volts, about 15% of the intralay coupling. You get a Hamiltonian, effective Hamiltonian, which is now 4x4. So there are two blocks on the diagonal, which just describe the two single graphene layers, and there is a coupling which is off diagonal. And you can see here appears in the basis that I'm using in the 1, 4, and 4, 1 elements. So this is 1 for the A side here at the bottom, and 4 for the B side at the top. So this is the simple coupling that you get. And you do the same procedure as before. You look for the energy eigenvalues. This is the energy eigenvalue equation. Lambda here is a spinor, so it has 4 components, and 2 of them they're simple. The first one you can always renormalize because this is a homogeneous equation. So the first component I set to 1. The third one comes out to be just a plus or minus 1 sign, and the non-trivial components are these two. If you solve for the energy, you find 4 bands. So 2 of these are the semi-metallic bands that touch, and I call these E1 bands, plus and minus depending on whether they are increasing or decreasing. Then there are also the E2 bands, which are separated by a gap whose value is 2 gamma. So the sigma here that you have in the fourth component of the spinor goes into a parameter that basically appears in the choice of the methods. Now, the key point here is that if you look at the bands, near the bottom of the bands, they all have a quadratic dispersion. This is very, very simple, but one can ask the question, is this quadratic dispersion the smoking gun of a non-relativistic behavior? So when I visited Camerino, I discovered about this. I had not previously worked with graphene, and the first thing that came to my mind is that the excitations here should be the non-relativistic fermions that I already knew about, the Lévy-Leblond fermions. And it turns out that this is true. So to show what I mean, basically I'm going now to do a low energy expansion around the bottom of the bands. I'm taking the momentum here, the momentum, this is a complex number here because the spinors are complex, but this is a kx plus iky. I'm taking the modulus of the momentum to be small compared to the gamma factor, which is the coupling between the two different layers. And if you do that, and you plug it in the spinor components, you get this result. I'm just displaying lambda 2 and lambda 3 because, as in the previous slide, the other components are trivial. So you plug everything into the spinor, and then I can show you the following with explicit formulas for one of the Dirac points. So we have 4 spinor components. I'm going to reassemble them to give 2 separate objects, which I call chi1 and chi2. They're time dependent. Each one of these objects has 2 components, and they're written here, out of the initial solution. If I take these 2 face value, they satisfy a set of coupled equations which are first order, which are called the Lévy-Leblond equations. And let me just switch for a second to this slide. I'll go back. This is Lévy-Leblond. He's a French physicist. He's written this paper in the 67. He was talking about non-relativistic particles. He wanted to find equations for quantum mechanics that satisfied Galilei. They were basically transforming under Galilei transformations instead of Lorentz. And he, in particular, he focused on the case of spin 1/2. He found an equation that basically is the limits of speed of light c that goes to infinity. It's this set of equations. It's the level equation that I showed you before. And for example, he found a very interesting conclusion. I don't know how many of you know about this. The Landé factor g equal 2 is still valid for this set of equations. It's not a relativistic equation. Many people believe it is relativistic because it comes from the Dirac equation, but it's in fact just purely quantum mechanics. So these are his equations, and the equations that I'm writing here are just the same, written with different conventions for the spinors. And what they do, they have, you see, they couple the spinors chi2 and chi1, and there's always a d operator here, which is the normal Dirac operator, acting on one of the spinors. But on top you have time derivatives, and on the bottom you have a mass parameter. The mass m here is really the non-relativistic mass, and for our system is proportional to the gamma hopping parameter. Now, so we can say first of all that we're finding these quasi-particles at the bottom of the bands. So they really are Galilean variant quasi-particles. Now, the interesting bit is when you start curving the surface, because now we have spinors. Spinors are not scalars, and spinors, they can feel the presence of a curved surface. So these are the same equations rewritten in the following way. I'm introducing a curved metric here in the covariant derivatives. The derivatives are now not partial derivatives, but they're covariant. And just for completeness, but we will not use this, I'm introducing a vector potential and a scalar potential. If we have external fields, we can deal with them as well. Other than that, they're the same equations. And now one does the following. It's a very simple operation that shows the strength of the approach. In the second equation, one solves for the first spinor as a constant times Dirac applied on the second. You take this and you plug it in the first equation. So in the first equation on the right, you get Dirac times chi1, and chi1 was Dirac chi2, so you get Dirac squared acting on chi2 proportional to times the derivative of chi2. So this becomes a Schrödinger equation, where everything is applied to chi2. I basically exchange a system of first order coupled equations. I exchange that for an equation that is now second order, but only for one of the spinors. Here E is the energy. This term here is like a p squared. This is just kinetic energy. V and B we can ignore. It's just the external fields. But here is crucially the term, which is the intrinsic curvature R of the surface. It's a scalar term, and as you can see, it goes directly into the Schrödinger equation. One can see immediately how this term behaves as a local change in the energy density. So this is really the main equation. From here you can read that when you change the curvature, I have here 3 cartoons of curved bilayer. When you change the curvature, you're acting on the bands. If the curvature is positive, you're separating the bands, you're creating a gap. Zero curvature, you're back to where we started, and a negative curvature, you're starting to overlap the bands. So at first order, you're now in a metallic behavior. So this is the key effect we're talking about for electronics. Quick remark: we don't want the curvature. We don't want the energy correction here to be too big. Otherwise, we go out of the limit that we're taking of low energies. This means small curvature, big radius of curvature. How big is that? Well, it should be bigger than 1.5 nanometers. So we consider deformations that are smooth on the scale of the lattice. At the same time, I want this to be big enough so that I can measure it, for example, with APES, so of the order of 1 millielectron volt. This tells me that I cannot have a curvature radius that is bigger than 23 nanometers, this is still okay because it's well within the typical curvature scale of graphene systems. So I see now that time is running short. I will not give you details about the four-dimensional space-time, but this is a picture of Eisenhardt. He used to be dean in Princeton. He was a person working in differential geometry. He basically laid the foundations for the results that we have. Is that I can take here in the flat case, just to make it simple, an x and y coordinate for our surface. It's a profound result. I'm not going to jewel into this. You can add two more coordinates and reconstruct a four-dimensional Minkowski space. And just skipping on all the details, I can guarantee that if you take the two Lévy-Leblond spinors and you compose them in this fashion and add a dependence which is on the v coordinate, one of these null coordinates, you get a result which is a spinor living in 4D and which is now massless. So in a way you're going back to the old story of massless spinors in graphene. Although now you have four dimensions because you have a bilayer, and in a way your spinors, they're kind of starting feeling that there is a transversal direction acting on them. This is just a nice, I don't have time to comment on this, but it's a very nice, the geometrical idea. If you take the Dirac cone in 4D, and you slash it with a plane which is parallel to one of the generatrices of the cone, as Apollonius of Perga told us 2,000 years ago, what you get is a parabola. This is the Galilean parabola of the dispersion, which is quadratic. So this is just a slide with the highlights of the work, reminding you about massive Lévy-Leblond fermions in bilayer graphene. They're there. And we have the Schrödinger equation with intrinsic curvature affecting the electronic states. These are the main points I'd like to stress. So I would like to thank you for your attention.
Okay, thank you. The talk is over for one question because we are running short of time. We have to.
So can you say how big? I mean, you said that the effect is just 1 millielectron volt if you would try to probe it.
Well, what I was saying here is, okay, so I have an energy which goes like the curvature, and this in turn is inversely proportional to the square of the radius of curvature. So the flatter I take the surface, the bigger the radius of curvature, so I get a smaller and smaller correction to my energy states. And I'm saying, if this is too small, I will never be able to measure it. So what's the best that I can do today? Something of the order of a millielectron volt. And how much curvature does this amount to? Something in the region of 20 nanometers.
But this is a tiny gap for your using.
This is of the order, if you want, of the ripples that you have in graphene.
But if you decrease from 23 nanometer to 1.6, you can increase up to 100.
Oh yes, yeah, absolutely, yes.
So this is the minimum will be 23 nanometer, but then if you increase the curvature, the gap will arrive to 100 millimeter volt. You can tune in a continuous way.
Exactly.
Changing the curvature.
So
we selected the physical interval of curvature to be measured.
Exactly. So this is the worst case.
Yeah, the worst case is 23.
Just a curiosity, what happens if you have a cylindrical?
Well, for a cylinder, you don't have intrinsic curvature. So the fact we're talking about is about the intrinsic curvature. So you probably will get only the strain effect, the Landau levels, but no gap opening.
Okay, thank you very much. Thank you very much. Let us go to next speaker.